The first of the two systems we'll be talking about in Chapter 5 is the harmonic oscillator. And this is, in the classical sense, sort of what we usually think of when we think of the harmonic oscillator. We have a mass attached to a wall, a fixed object of some sort via a spring. Another way of modeling a harmonic oscillator is a pendulum swinging. Harmonic oscillators show up in many different situations in physics, and probably you've already seen this in your physics classes. And so the important thing is that how we model a harmonic oscillator is we use Hooke's law, and this will apply also to bonds, right? So this is how we model springs, but we use this as our first approximation for bonds as well, which is that the force exerted on our mass is going to be proportional to some constant that we call K times X, where X is equal to how much the spring is stretched. And so this X is equal to 0 when the spring is at rest, and then if it increases if we stretch it to the right, and it decreases if we stretch it to the left. Okay, and so from this we can, from this model, the thing we need to model this quantum mechanically is we need to know what's the potential energy. Now obviously potential energy is going to depend on the on X, right? So it's going to depend on if we have the spring stretched out, that should increase the potential energy. And same thing if we compress the spring, that should increase potential energy, because there's going to be a force pushing opposite of the direction. Either when we stretch it out, it'll want to pull it back in, or if we compress it, it'll want to push it back out. And so the potential energy is going to depend on X, and we can actually find it from this force equation up here, right? So the relationship between potential energy and force is that if we, let me just look at my notes here, is that the force on a system depending on X is equal to the negative of the derivative of the potential energy with respect to X. So that means if we integrate both sides here, we should be able to figure out the potential energy. So if we do this integration, we'll get v of x is equal to 1/2 k times x squared plus a constant. And so we'll set this constant to 0. And so this is the potential energy for a classical harmonic oscillator, and also will be true for our quantum harmonic oscillator as well. And so this is what we need to put into this will go into the Hamiltonian, and that will go into the Schrodinger equation, and that's what we're going to be solving to find the wave functions and energy of the quantum harmonic oscillator.